Just another example where we use the equation of continuity and the Navier-Stokes equation to solve a problem. Okay, and of course you're trying to practice what we've discussed here in the second problem of this new assignment. Okay, so in that problem you will need to solve a ODE that's a little more complex than what we've seen before. Okay, but you should be okay, all right? So then we were discussing the cell segmentation problem. So this is related to the ESR test in the hospital in case you occurs. So this is when that test is being done. Okay. You see these copper tubes. So what you do is basically to put some flow in this tube and look at how the red cells study in this tube to the bottom. So of course that's the motivation for us to discuss this problem. To look at how cells move in a large volume of fluid. Okay, so to do that, of course, we started with a sphere, which is more like a white blood cell. Okay, and look at when it's moving in a large volume of fluid, what kind of resistance it's going to experience. Okay, so and of course, then we did sort of the coordinate transformation sort. Okay, instead of looking at the sphere moving in a large volume of fluid, we're looking at the fluid flowing around the sphere. Okay, so velocity and the pressure. Okay, so using these, of course, we can calculate all the shear stresses and normal stresses anywhere. Okay, so these for non-zero, all others are zero. Of course, this is why we're looking at this. We want to look at the resistance or the force experienced by the sphere when it's moving, or the other way around. Okay, or the force experienced by the sphere when there's a fluid floating around. Okay, so basically this is the resistance, right? Okay, especially this force I'm talking about, of course, is the force in the z direction, because see, when the fluid flowing in the z direction, of course, we expect that the force applied by the fluid to the sphere will be in the z direction. Okay, because if you look at this sort of from a spherical coordinate perspective, okay, you know this problem has symmetry about phi direction, so no force in that direction. Okay, all right. So mainly the force should be in the z direction. So now we want to calculate this force. The force is exerted on the sphere in the z direction. Okay, so all right. So how do we do this? So that's the z direction. Okay, so the fluid is flowing in that direction. To calculate the force that's acting on the sphere, of course, we need to calculate what? All the stresses and pressures acting on the sphere, because these are the ones that are basically the forces applied by the fluid to the sphere, right? So we know in general how these stresses are calculated, right? So these, remember, can be used for calculating the stress in anywhere of the flow field. And now we just need to know these stresses on the spherical surface, okay? All right, of course, you know, although on the spherical surface, all these little r's, okay, and there, these r's will be equal to the radius, okay? But still, these stresses, including the pressure, they are not constants, okay, because of this statement, okay? So that means on the spherical surface here, the stresses and pressures, they will not be constant. So when this happens, of course, when you try to calculate the force from the stress, and then it takes a little effort. When the stress is a constant, you know that's easy, right? To get to the force, if the stress is a constant, all you need is to multiply the stress by area. That's it, right? In that Coulter-Visconti example, if you calculate the moment, since the stress is constant on the cylinder, all you need is to multiply the area by the stress, get force, and then times that with the moment arm, you get a moment, right? So, however, the stress is not a constant here, okay, on the surface, all right? Okay, what do? How do we get to the force from the stress if the stress is not a constant? Well, if it's not a constant, can we consider a small area on the spherical surface? Well, since it's a small area, we can consider the force, the stress there as more or less a constant. We can multiply the stress and the area together to get the force, right? And then we can calculate the component, the z component of that force in the z direction, right? So force, that's just a small area. And we do this for all the small areas on the spherical surface and add them all together, okay? So that'll, as long as this area is small enough, that'll translate that summation to what? Integration, right? Okay, so that's what you need to do, all right? So the stress is not a constant, all right, on any surface. If you want to find out the force, all you need to do is to do a surface integration, okay? So basically it's like tau times dA over the whole surface, okay? All right? So of course, the stress here, for tau r theta, this is one of the stress components, which is not zero, okay? So you see all these, r theta, phi, and r theta. Now for phi, okay? So that's the stress in the phi direction, okay? All right? So it goes around. So phi direction here, it will go in, here it's going to come out. So it goes around. That means what? That stress, tau phi will have no contribution to the force in the z direction, right? Okay, so that one is gone, okay? All right? So let's look at tau r theta. So tau r theta stress. Since right now we don't know whether it's larger than zero or less than zero yet, to draw its direction is important because when you calculate the z component of the force, right, you need to know the direction of stress. If you draw it wrong, of course, you'll get the wrong component, okay? So before we know it's positive or negative, we assume it's positive. If it's positive, so tau r theta, in which direction it points to? Up or down? Anybody? Huh? All right, so tau r theta, we know there's stress on the spherical surface, right? One of them is tau r theta, okay? So if because, when you write the symbol, before you know it's positive or negative, we always assume it's just positive, okay? So this is, tau r theta is positive, larger than zero. So the question is, on this surface, on this spherical surface, if it's larger than zero, the stress, is it pointing up or down? relatively set up. Another, well, it's either up down, or down, right? Okay. So in this case, it is up. Okay. Now the reason, of course, I don't really want to repeat this anymore because I've repeated this so many times. All right. So if you don't know why it's up, well, I guess you need to talk to me. All right. We also have tau RR. So tau RR, of course, will be either in negative or positive R direction. So is tau RR pointing in the negative R direction or positive R direction? Assuming it's positive.
Negative.
Negative. Okay. So very good. And there's also the pressure. That's easy because pressure always perpendicular to the surface and going into the volume of whatever you're considering. In this case, it's the sphere, of course, going in. And that's the pressure. Okay. And there's the tau theta theta too. Okay. So tau theta theta. Is it acting on the surface? We have 4 components that are not 0, right? So, all right. So these are the stress components and the pressure. Okay. So we talked about this one. It's gone, right? No contribution to the force in the z direction. We drew this. We drew this. Now, what about this one? We also drew the pressure. Does this have any contribution to the force applied by the fluid to the sphere in the z direction? On this surface, how many stress components should we have? 3, right? Because this surface, the normal direction of the surface is always in the R direction, right? No matter where you're looking at, right? So the normal direction is always in the R direction. So 3 stress components. We talked about 2. The third one is tau R phi, right? That one is 0, okay? Tau theta theta is not really acting on the surface, so, okay, all right? And the same goes with the tau phi phi, okay? So they are not really on the surface, of course. When you calculate the force that's applied on the surface, well, those components, they're gone, okay, all right? All right, so that's it. These are all the stresses. Now we just need to do the integrations. So first, we can look at these 2, okay? P and tau R because they're pointing in the same direction. So remember, we're looking at the component of the force in the z direction, okay? So for a spherical surface, all right, we know that when you try to calculate the force, will be something like this, okay? Stress times dA integral. You'll get the force, right? Once you have the force, in this case, of course, for these 2, because they are not pointing in the z direction, right? If you're looking for the z component of the force, then you need to look for, well, the z component of the force. To get the force, all you need is what? Well, times the cosine theta, right? Okay? So, and it points to the negative z direction. Anyway, so how do you write a dA in this case? It's a spherical surface, right? Okay? So basically, the dA here, because on the spherical surface, R is a constant, okay? So that dA will come when you vary the other 2 coordinates, theta and phi. So one of the line segments when you vary theta is, so basically when you vary theta, which is this diagram here, that line segment you will get as well. The length of that arc is r d theta, right? Okay, so this dA here one of the line segments are d theta. Okay. Now the other is what? When you vary phi. Okay. When you vary phi, again, if you have trouble visualizing this, you need to refer to those two figures, MATLAB figures I uploaded on campus. Okay. So you can see how when you vary these different coordinates, how you get these line segments. Okay. When you vary phi, you get another one. There, that radius is r sine theta and d phi. So this is the length of the other arc you will get when you vary phi to get d phi. Okay. So of course, the product of these two will give you a dA in this case. Okay. All right. So that means when we integrate with theta and phi. So for theta, it's from 0 to pi. For phi, it's 0 to 2 pi, and that's the that's the integration. Okay. So of course now the forces. So this means, I guess I could also write as P, vertical line, R equal R, write two separately, but I wrote this together, which this means the values of these pressure and stress on the spherical surface, okay? So we know this times the area, which is dA, those will give us the force, right? However, you can see here, that force will be pointing to this direction, okay? To get the z component, we need to multiply by cosine theta, and it points to the negative z direction, which is why you have this minus, so that you can get a positive component, okay? So this times cosine theta and dA. So let me move this up. So the dA, sorry, square, is r d theta and r sine theta and d phi. Okay? All right? So again, negative because the force points to the negative z direction. To get the positive component, you need to add the negative. Cosine theta, that's the z component of the force, and that's the dA. The integration of the whole surface area. Okay? All right? So this whole thing is basically from here. All right? So of course, now we just need to plug in everything. Okay? And we know the expressions for the P and also for tau RR. So you plug them in. P0 minus rho G R cosine theta. Now, you may remember this was a Z before, okay? All right? So Z on the spherical surface basically becomes R cosine theta, right? Okay? So you can see it from here. This point, Z is basically this. So that's why it's R cosine theta, okay? So for the dA, or the product of these two line segments, we can just write it, r squared sine theta and d theta d theta. Okay, so this cosine theta is here, and this is the sum of these two. Okay? Yes?
What is that? Is that u times v sub?
V infinity, V. So that's from tau RR. Okay, so basically, as you can see here, where is it? So for tau RR, remember now we're on the spherical surface, right? So this lowercase r is basically capital R. So this is R, of course, this is R. And you add this together, you have 3 mu infinity divided by R and something, right? And you look at this term, it's the same thing. Not the same thing, similar, okay? So little r will be equal to capital R. You get something similar, you add these two together, you get that term there, okay? This last term here, okay? All right, so of course then integration. So P0 times cosine theta, sine theta, as you know, so for, so it's just a sine 2 theta, right? Divided by 2. And cosine theta, well, anyway, it's just a trig integration, right? So, and in the end, it's just the integration of these two terms because they both have cosine theta and constant, right? Rho g are constant. This is a constant. So basically, it's constant times cosine theta. Now for P0, the integration here will be 0 because, as I mentioned earlier, you basically have cosine theta times sine theta, which is half sine 2 theta. As you know, for sine 2 theta, pi is 1 period. Okay, so for 0 to pi, you get 0. Okay. So that's why you don't see P0 here anymore, okay? You basically have only this integration. So you integrate that, you get this, okay, from 0 to pi, of course. For phi, it's basically 0 to 2 pi, because as you can see here, it does not depend on phi, so it's just 2 pi, okay? All right? That's why you see this 2 pi here, that's basically phi, okay? All right? So, of course, plugging all the numbers, you'll find out this is equal to 4/3 pi r cubed rho and g plus 2 pi and mu v infinity and r. So 2 terms, okay? Now you look at the first term here. Basically, this is what? The volume of the sphere times rho and g, right? What is that? It looks like a weight, right? Okay. What weight is that? Is that the weight of the sphere? Well, to know what it is, you need to know what this rho is, right? So what is that rho? Is that the rho of the sphere, or is that the rho of the fluid? Fluid, right? So this one means what? This is the weight of the volume of fluid expelled by the sphere, right? That's what? Buoyancy, okay? Okay? So that's due to the pressure, basically buoyancy, okay? So this is the buoyant force, pressure in the fluid, okay? The second term here is called the form drag, okay? All right, so we've done part of it, okay? We've done these two, and now tau r theta. For tau r theta, of course, the dA is the same, and the integration is also the same. The only thing different is how the force is calculated. So on the surface, because now you can see this force will be pointing to that direction, it will have a positive z component. So then you don't have this negative sign anymore. So all we have is r theta at r equal to r times, now this time is sine theta for the z component. See, because it's pointing to that direction, and when you look at this angle here formed between the stress and the z direction, that's theta. So, and the z component, no, sorry, that is the cosine theta. That is the theta. Okay. So basically, when you look at this stress here, so that's theta, and then this means what? This means that angle is theta. Let me draw this a little longer. So r theta so that's why the z component would be sine theta. And of course, the rest of it is dA, okay? So copy all the dA there. We know it's basically r squared sine theta and d theta and d phi, right? Okay, so, and as you can see here, the most important thing is to come up with the correct equation, okay? The correct terms, correct units, correct directions. So after that, it's just math, okay? So, and now we plug in the numbers. So tau r theta at r equal to r, capital R, is this much sine theta, and then sine theta, r squared, sine theta, d theta, and d phi. So just like before, it does not depend on phi. So again, integration about phi will give you 2 pi. Okay. So then the rest of it is to integrate theta. Okay. So and then you have is mu v infinity r 2 pi. That's the phi. R squared, that's the constant, and then negative cosine theta, a third, cosine theta cubed, and pi, and 0. You can kind of see that, right? So, okay. Yeah. And of course, this will give us 4 pi mu r v infinity. So this is the second part of the drag. Now this is called the friction drag. Now, why it's called the friction drag? It's all about the direction. Okay. So look at the direction of tau r theta. Of course, it's like what? This is like the shear drag, right? So it's like the fluid is moving tangential to the surface, so it's like friction. Okay, that's why it's called the friction drag. The previous one, the form drag, well, it's basically that. That one is basically due to what? The shape. Okay. So, all right. So we have the form drag and the friction drag. For us, we have the buoyancy. Okay. So if you take out the buoyancy and add the other two together. So overall, first of all, this is the component of the force. I mean, this is the z component of the force acting on the sphere, 6 pi mu r v infinity. So that's the total. And if you take out the buoyancy, what's left is called the kinetic force. So buoyancy is always there, okay, whether the fluid is moving or not. So you take out that, what's left is called the kinetic force due to the flow of the fluid, okay? So this force, F sub k, is 6 pi mu r v infinity. And this is a very classical equation. It's called the Stokes law, okay? So basically it's the drag experienced by a sphere when it's moving in a large body of fluid, or the other way around, okay? I mean, if you consider this as a large body of fluid moving around the sphere, that's okay too. The same equation for the resistance or drag, okay? All right, since our goal was to use this problem to look at the cell sedimentation, and we know that red cells, they are not really spheres. So what do? For other shapes, and we can approximate red cells as disks. That's a sort of like a first approximation. And of course, the disk will have a radius r. And then the resistance can be calculated using this concept. That's called equivalent radius. So in this case, the force, the drag force F sub b, can be calculated by 6 pi mu r spes v infinity. So this r spes is called the equivalent radius, or again the name Stokes radius. So this is basically what people did, okay, for a disk or many other shapes, okay. For low Reynolds number flow, like in this case, because the whole left-hand side of Navier-Stokes equation is gone, there are many ways to get the analytical solutions for these standard shapes, okay? So you solve that problem, which is not easy, and then you'll come up with a resistance, right? So then you can calculate the equivalent radius, okay, for many shapes, okay? So of course here we don't really care about many others. So for red cells, the first equivalent radius is 8 over 3 pi r, okay? And this is approximately 0.85 radius. So as you can see here, it's smaller than the sphere, okay? It's about 85% of the drag experienced by a sphere with the same radius, okay? All right? This is when the disk is moving orthogonal to the flow. In other words, the disk, okay? I mean, if you consider the screen here as the disk, the flow is in that direction. Okay. So of course, then there's another value here, which is 16/9 pi and r, and this one is about 0.57 r, and this is when the disk is moving parallel to flow. And obviously, when it's moving in parallel to the flow, of course, you should expect less resistance. So it's about 57% of this drag experienced by the sphere with same radius. Okay. All right. So with this, actually now we can look at how a cell moves in a large body of fluid. Okay. So for now, we'll just look at one cell. We'll look at a simple case here, which means we're going to look at the sphere. Okay? All right. So when you put a cell in a fluid, okay, say a white cell, okay, when you put a white blood cell in plasma, for example, okay, assuming the plasma has a large volume, what's going to happen? Say the gravity is pointing down, okay? So gravity is in the z direction, okay? So what's going to happen to the cell? It's going to start to move, right? So you put it there. At the beginning, velocity is 0, but the gravity will accelerate the motion of the cell, right? So once it starts to move, what's going to happen to the drag experienced by the cell? At the beginning, it's not moving, so there's no drag on the cell, right? So the gravity will pull it down. It's going to start to move, and then the cell will experience the drag, right? Actually, the faster it moves, the larger the resistance, right? Eventually, the gravitational force, the drag force, and the buoyancy will reach equilibrium. Okay, that's the steady state. Okay, so that's basically what happens, right? So to look at its motion, of course, you know, to look at how the sphere or the cell moves, we need to use Newton's second law. Basically says force is equal to mass times acceleration, right? So volume, rho, sphere, mass, acceleration, dv dt is equal to the force. So the force, gravity is accelerating the motion of the sphere, and there's the drag. Okay? And that's the total drag, of course. Okay? When it's moving in a large body of fluid. And of course, we know the right hand side, if you plug in the drag, and then you'll have rho sub s minus rho and g, and minus 6 pi mu r and velocity. So this velocity here is the instantaneous velocity at any time point, okay? All right? So that's not just the v infinity or the velocity at steady state, because see, we're looking at the whole process. Okay, starting from 0 velocity and gradually, okay? All right? So we can solve this equation, right? So constant, velocity, right? So all you need to do is to divide both sides by this. So put the velocity on the left-hand side, 1 over this, and dt on the right-hand side, and this on the right-hand side, okay, and integrate, right? So you know there will be a log term and stuff. So dv divided by that. And then dt divided by this. So now you can integrate, right? On the left, you get a log something. On the right, you get a constant, okay? So that's how it's solved, right? So you have a negative 6 pi mu r in front of v. So the first thing you want to do before you integrate is to try to change this v into something that's the same as this, right? So basically multiply negative 6 pi mu r there so that this dv becomes d whole thing. You do that, you do the same, you have to do the same thing on the right hand side, right? And that's how we got this negative 6 pi mu r, okay? And then you integrate, this is a constant, so it doesn't matter, you can put that constant there too, you get this log, right? So t plus the constant, okay? So of course, now we need to determine that constant, right? How do you determine that constant? This is an equation about its time dependent, right? Instead of boundary conditions, now we need initial conditions. What's the initial condition? Well, basically at t0, right? So what's at t0? At t0, what's the velocity? 0. There we go. So then you can determine c1, okay? And so you get that constant, and then eventually, once you have that constant, of course, you can solve for velocity, okay? So it's basically E for everything there, and then you move this to the other side and divide by this, okay? So velocity is equal to 2r squared rho s minus rho g 9 mu 1 minus e the minus 9 mu 2r squared rho s and t. Okay, so that's the velocity, how the velocity of the cell will change over time. Okay, so obviously you can see here when t is equal to 0, this is 0, initial condition. It's good. And then when t goes up, okay, so this exponential function will go down, right? Because it's 1 over exponential 9 mu and stuff. So 1 over e that, so that's less and less when t goes up. So that means what? This will increase, right? That means, well, when t goes up, velocity will be larger and larger. However, when you see this e to the negative something t, you know that when you draw this, it will look something like this, right? So although velocity will be larger and larger, but once it is increased to a certain point, the change will be very, very small. Okay, so it approaches to a constant value, and that constant is, of course, when t is equal to infinity, this is 0, and that's that constant. So that velocity is the terminal velocity. So basically this thing here is the terminal velocity at t goes to infinity. So let's call that v sub t. Okay? And of course, it is equal to 2r squared rho s minus rho mg 9 and mu. Yes?
So v sub t is different than v infinity?
V what?
So v sub t, if there is different than v infinity?
You can consider v sub t as v infinity too. Okay? All right. So another constant that's of interest is this constant. Okay? What do you think we should have the unit for that constant?
1 over s.
1 over time, right? Okay? All right? That's because, see, e to the minus, this has to be dimensions, okay? So that means this should have the unit of 1 over time. Of course, you reverse that, you get the unit of time. So 2r squared rho s over 9 mu should have the unit of time. We'll call it t sub c. We'll call this the characteristic time. So the so-called characteristic time is sort of like a scale for time. So once you know the density of the sphere, radius of the sphere, and the viscosity of the fluid, okay, and then you can calculate this time. This time represents the time it takes for the velocity to reach a velocity that's close to the terminal velocity. How close? It's about 70%, okay? All right? So it's about 70% of the velocity, terminal velocity, after this time. Okay, so that's the characteristic time. Okay? All right? So of course, once we have these constants, you can write the velocity as v sub t, y minus e to the minus t over t and c. Okay? And now let me give you some numbers. I'm using r equal to 10 micron, which is a little overestimate of the radius of a white blood cell. A white blood cell probably will have a radius of 8 micron around, okay? So of course we know this is 10 to the minus 2 millimeter and 10 to the minus third centimeter. That's the radius of the cell. The density of a white blood cell, it is indeed slightly larger than water or plasma. It's around 1.05 gram per centimeter cube. That's the density. And for mu, for plasma, it's around 1.2. Well, we'll just use 1. Okay, so it's not that far off. So with these, we can calculate Tc, right? Which is right here. Okay? So find out Tc is about 2.3 times 10 to the 5th second. What does this mean? You can see that it takes little time for this process to reach more or less the steady state. Okay? So as I mentioned earlier, after this time, the velocity of the cell will be equal to about 70% of the terminal velocity already, okay? You give it a little longer, like twice as long, it's going to reach 90%, right? Okay? 3 times as long, well, more or less, almost 100%, okay? So that means it takes a little time for this process to reach the steady state. And that's the signature of a low Reynolds number flow, okay? So as I mentioned before, when you look at the motion of cells, of the molecules, these small things in fluids, like water and plasma, very likely it's going to be a low Reynolds number flow. That's because the scale is so small, the length scale, okay? All right? So for low Reynolds number flow, as you know, we can ignore inertia, right? The whole left-hand side of Navier-Stokes equation is gone. So it's going to become a steady state problem. This is why. It's because it takes a little time to get to the steady state. Okay? For the density of the plasma, and we can just use 1, like water. And for G, we can use 980.665 centimeter per second squared. And now we can calculate the V sub t, the terminal velocity. We'll find out this is about 10.9 micron per second. Which is not a small velocity compared with the size of the cell, okay? As you can see, the cell is about 10 microns. So in 1 second, it can move basically its own size that much, okay? All right, so compared with the size, this is not a small velocity. However, you use these velocities and calculate the Reynolds number, you'll find out it's going to be a very small number, okay? All right, so, and we won't do that because it's a simple calculation, okay? All right, so let me summarize what we went through in the last few lectures. So we used the shell balance method and derived the equation of continuity and the Navier-Stokes equation, right? The reason why we did that is so we didn't have to go through the shell balance method for every problem, like these, okay? Because for many problems where we have a constant rho, we have a constant mu, so that for these fluid flows or momentum transfer in these fluids, we can use the equation of continuity and then Navier-Stokes to solve for velocity, solve for the pressure, and we can solve for stress, everything else we want to calculate for momentum transfer problems, okay? So after that, we looked at a few examples, okay? So tube flow, Kuta flow, and the cell sedimentation, okay? So in your next assignment, you'll get some practice on this stuff, okay? All right. So this is sort of one module. I don't know. Anyway, so we're going to start a new topic. But before I do that, any questions about anything with topic? No? All right. Let me tell you this. So the exam is about 10 days away, right? More or less? Okay. So yeah, let me bring up the syllabus. Okay, so we're here, and the exam will be here. So 1 week, 2 weeks, 3 weeks. So better than I thought. And better than you thought too. Anyway, so since the exam is going to be on a Thursday, okay, and this Tuesday, at the start of this lecture, I'll start with questions. So basically, if you studied before this date, so bring your questions to that lecture, okay? And if you don't, of course, we'll just move on to the next topic, okay? So we'll use that sort of like a review, okay? This means that please study before that date, okay? Otherwise, there'll be no questions, and then, of course, I guess you won't get no chance to ask questions. So.
Will material on the exam go up until the Thursday the 28th?
That's a good question. So I'll let you know somewhere around here what the exam is going to cover. Okay, so yeah, it's going to be very close to somewhere here. Okay. All right. Okay. So just want to let you know. Just want to let you know that that Tuesday will probably be like a review. Okay. Yes.
Will we be getting an equation sheet?
Oh yeah. So that's a good question. At least 1 week before the exam. That means that Thursday. Okay. The Thursday before the Thursday where the exam will be, I will let you know the equations that you will be given. Okay, so you get a copy of that during the exam. Yeah. All right. So exam is closed book, closed everything. Calculator is all you need. Okay. All right. Okay. So our next topic is dimensional analysis. What is dimensional analysis, and why do we need to learn dimensional analysis? So a little motivation. I'm sure you saw this movie, or something similar, because this guy appeared in many movies. So, you know he's bigger, right? So, now the question is, say you're given the task of designing something like this, okay? All right? Assuming you have all the parts you need, okay? Can you just say, well, let's say you want to build this guy 3 times or 5 times larger, okay? Of course, one thing you want to make sure is that, well, indeed, all the lengths will match, right? In other words, his height should be 5 times higher, and the size of the hand and everything. That's the first thing you want to make sure it matches, right? So, what's the second thing? Or are there other things that we need to be concerned about, or trying to make a match other than the size? Well, that's why you want to learn dimensional analysis, okay? Because there are indeed other things you should consider other than just the size, okay? Now, of course, this is just one thing that where dimensional analysis can be potentially used, okay? So dimensional analysis did not start by considering sort of things like this. Instead, it was sort of developed because of other reasons. Sometimes you want to build something like Hulk, okay? Or another example is a aircraft carrier, okay? All right, so in that case, you know, that thing you want to build is also very large, okay? So to look at how that carrier, or maybe even an airplane, or large aircraft carrier, to look at how it's going to perform once you actually build it, okay? Sometimes it's very hard to build a model first and look at how it's going to perform, okay? So sometimes we cannot obtain data from the actual device to be built. Well, if you cannot do that, or if it's too costly to do that, are there better ways? Yes. So instead, you can do this by using smaller or larger models. So depending on that's something you're going to work on is small or large. So instead, we can obtain data by experimenting on a model device, which may be small or smaller compared with the original. Of course, one of the examples is aircraft carrier. Or you can look at the case of Hulk too, because the question here becomes whether the data we obtain from humans can be used for Hulk, okay? So, or sometimes this model device is actually larger. So the model device could be larger or smaller. Now, when this model device will be larger? Well, I'm sure you heard about this micro or nano fluidic devices, right? So there, we're trying to build small things to do what large devices can do. So of course, sometimes these small things, it's very hard to evaluate. So you use larger models, okay? Anyway, so these models could be large or could be small. Now, of course, how can you make sure the data you got from the model device can be used for the actual device? Well, we mentioned one thing, right? To make sure, to ensure the same performance or flow. Or in other words, to figure out how we can use the data obtained from the model device, we need to use dimensional analysis. We make the model device and the actual device to have several similarities. The first one is geometric similarity. Well, this is something that we expect, right? So your model device has to be geometrically similar to whatever device you want to build, right? So in other words, you can see, so Hulk grew sort of in ratio, okay? So basically, it still looks like a human being, although it's larger, right? So that's geometric similarity, okay? But that's not enough, okay? The second thing we need to make sure that they are similar is kinematic similarity, okay? So we'll define this one later. And the third one, which is more relevant to momentum transport, is called dynamic similarity. All right, so geometric similarity, to express this in terms of math, it simply means that, you know, if this is device 1, and this is device 2, no matter which one's model, which one's the actual device, one is smaller, the other is bigger. If, say, this dimension here is B, and this length here is A, geometric similarity means that the ratios of these two in the model device and in the actual device, they should be the same, okay? So that's sort of the mathematical interpretation of geometric similarity. However, this is not enough, okay? Why? We also need kinematic similarity. Kinematic similarity exists when in geometrically similar systems, like those two. Although I drew two simple diamonds, but you can always, you know, imagine these two could be one small human, the other is bigger, one big aircraft carrier, one small one, model, okay? So in these systems, like 1 and 2 shown above, or other complex ones you can imagine, okay? So kinematic similarity will require the velocities at the same locations are related according to the following relationship. For example, if you have 3 velocity components, kinematic similarity requires that these ratios be the same in 1 and 2. So this first, second, so the same location, okay? At different locations, of course, this ratio may be different, but they have to be equal in the two devices. Of course, we won't have to write the third one. These two guarantees what? Vy over Vz, the two in the two devices, the same location, they're the same too. Okay? Now, as you can see here, for example, again, if you look at the blood flow in Hulk and a normal human being, okay, if you want to require kinematic similarity, you don't really have to require that the blood flow of Hulk has to be 5 times larger than the human being, okay? All right? Although, you know, the blood vessels, because of geometric similarity, they have to be 5 times larger, okay? Now, for kinematic similarity, all you need to require is that the velocity ratios are the same, okay? For example, if you look at the maximum velocity of the blood, you know, in one blood vessel, you look at the maximum velocity in a normal human being of the same blood vessel at the same location. All you need to require is the ratios in these two systems are the same. In other words, they don't have to be, I mean, yeah, so all you need is the ratios are the same. That's it. That's the kinematics now. Okay? All right? So, again, this is not enough because this does not guarantee these two systems are comparable in terms of momentum transport. And so because of that, we also we also need to require dynamic similarity. So what is this? Dynamic similarity exists when in geometrically and kinematically similar systems. The ratios of significant forces are equal. So that's dynamic similarity. Now, we cannot just write 1 or 2 equations here because, as you know, in any system, there could be quite a few different forces, okay? And no matter how many forces you are considering in that system, okay? For example, for a fluid problem, you may have 2 different kinds of inertial forces. You may have pressure force, gravity, viscous force, and if you have to consider electromagnetic forces, so there'll be more, okay? So no matter how many forces you are considering, as long as they are significant, which means you cannot ignore them, okay? Then these ratios of these forces, they have to be equal, okay? So when this happens, these two systems will have the same sort of dynamic performance, okay? So that means these two systems are similar to each other. In other words, whatever data you can get from one system can be easily used in the other. In other words, whatever data we have for humans, okay? And we can use them, we can easily use them for Hulk, okay? All right? So, of course, you can see here, the first 2 are really easy, right? So just the velocity ratios and dimension ratios, that's it. This one's hard. This one is the one we need to learn how to do it, okay? Now, there are 2 ways we can do dimensional analysis, okay? Now, one way is when you know the governing equations of any problem, okay? So if we know the governing equations of the problem, of course, here we're talking about momentum transfer, okay? So, and the governing equations meaning that you know the governing equations of the ones we use to solve problems, basically. So these ratios, meaning the ratios of forces and everything, can be obtained by non-dimensionalizing the equations. With appropriate scaling factors. These scaling factors are similar to the fundamental units of the unit system. All right? So basically what this says is that if you know the equations, okay, like if you're trying to look at the blood flow of Hulk and the blood flow of humans, you know what governs the blood flow, right? So basically the equations we've learned. If you know these equations, there's one way to do the dimensional analysis. That is, you can non-dimensionalize the equations. How can you do that? Well, you basically do that by choosing different scale factors for velocities, lengths, time, and everything you have to deal with, okay? So you choose these factors and make all these variables dimensionless by dividing the variable by the scaling factor, okay? Now, of course, these scaling factors, they are similar to the fundamental units of the unit system. Why? We'll discuss that next time, okay? So.